Hello, everyone. Pleasure to be here. Yeah, let's see if we can load them. Sure. Let's see if this works. This is the hard part of the presentation. So my goal today is to help you understand what's doable today when you're looking at medical text. So clinical content, biomedical content, and hopefully help you get your projects done. This will apply also if you're in other industries, so if you're in finance, in legal, anything where you're trying to understand text that's kind of specific to an industry that's not general English, and you want to do it quickly and well. So this will take a while. Just tell you when to switch. Okay, got it. So I'm from Johnson Labs. We are most well known by far for the Spark NLP library, which is a free and open source library that for the past 4 years has been the most widely used NLP library in the enterprise. Specifically within the healthcare space, based on the latest industry surveys, almost 60% of teams use it. So we've been fortunate really to see a lot of use cases and to see a lot of different ways where people are trying to apply deep learning, transfer learning, zero-shot learning, current technologies in the healthcare space. And hopefully this means that I'll be able to tell you more about different kinds of things you can do with this technology. So the first thing to know about healthcare is that when people write anything that relates to healthcare, they're not really writing it in English. They're writing it in one of really more than 100 languages that are super healthcare specific. And it's fair to call them languages because they have a different vocabulary, different semantics, different meaning, different grammar. And really, I mean, as you may know, it would probably be easier for you to learn Russian or Portuguese than it would be to learn how to read pathology reports or radiology reports. It takes just about the same amount of time. Click. And here are a couple of examples. This is from a public case study we had with the Kaiser Permanente. They were looking to build a system that would be able to predict how many open beds am I going to have in a hospital in the next shift, next 2 shifts, and how many nurses do I need of which type. So there's a lot of structured data to help with this, but one of the problems is the people in the emergency room. Because if I go into emergency room and I have acute abdominal pain, so I have a really severe stomachache, it could be anything, right? Maybe I'm going home 3 hours later, maybe I'm staying for 3 weeks. The only real clinical information you have is looking at the triage notes, so the quick notes that people write while I'm in the emergency room, and this is how they look like. So as you can see, this is very typical. None of the sentences are actually valid English sentences, grammatically. They use the wrong grammatical patterns, right? So since yesterday, 10/10, constant Tylenol 1 hour ago. So 10/10 is level of pain. Tylenol is what the person took at home before they came to the ER. And then the indication of kind of where it hurts. It never uses actually the words pain or patient, right? Because it's obvious from the context. You don't go to the ER, for the TV. And here's what we need to extract. You want to extract structured, clean features that you can use for prediction around, what hurts, where does it hurt, when did it start, what did you take at home, right? So you can actually make those associations, right? So those are the things that kind of this software tries to do. Here is another example. This is also from a public case study, work we've done with Roche, the pharmaceutical company, and they do a lot of work on cancer. So being able to look at cancer patients and, for example, match them to clinical trials, recommend the best next action based on kind of the latest research, match people with specific clinical researches applicable to them. And as part of it, you need to be able to extract information, in this case from a pathology report. So pathology report is, let's say you have something, people take a biopsy, take a sample, they send it, and then you want to understand what kind of tumor a person has. And the features we are trying to extract also are very specific. What's the staging? What's the histology? What are the margin? Where exactly in the body this happened? What are the biomarkers? And as you can see, there's another small challenge here, which is this is also a computer vision problem or an OCR problem, right? You have handwriting, you have markings. You have a mix of handwriting and print and text that you need to be able to understand in order to do this well. Okay, so then this is and another thing. I mean, if you read these things, really you need a medical degree and a lot of understanding to even understand when something is wrong or not. So there are 3 tools that I'm going to talk about that in combination can enable you to do this well and do this in one line of code. One of them is Spark NLP for healthcare, which is a software library separate from Spark NLP that focuses on giving the industry state-of-the-art clinical and biomedical NLP. So because it's a different language, really there's a different set of algorithms. There's a different set of medical conferences, benchmarks that people work on in this space. And what we do here is we look at the many papers, libraries, models that come out every week. We see if they're reproducible, if they're generalized. If so, our job is to give the industry the production-grade, trainable, scalable versions of these models, right? So basically, the main promise is that this will keep you at the state of the art as months and years come by. That's one. The second, no, go back one, you missed. No? Next? Okay. The second tool that we have is the NLU library. The goal of the NLU library is, and this is a Python-specific library, whose specific goal is to enable you to make use of all of these amazing models, really in one line of code. So what you can do here, can you press once? Here. And you can see some code examples. The NLU library has really 2 important methods you need to know, load and predict. And you can see an example, let's say on the right, NLU.load, and we tell it which model we are interested in. There are several thousand models that are available out of the box, and you can train your own. .predict, he are moving here, and it can correct it to, for example, he is moving here. As you can see here, you can correct your grammar, you can change your writing style, you can do translation, you can do question answering, you can do fake news detection, sentiment analysis, name entity recognition, and several thousand other tasks out of the box. So what load does, it loads the models, the embeddings, the pipeline, whatever is necessary. And then predict actually applies it. You can apply it on single text, as in here, or you can apply it on a full, just a Python data frame, and it gives you a data frame back. Or you can also apply it on a Spark data frame and just actually run this on a large cluster, right? So no code changes are necessary to scale this. And NLU is completely open source. Okay, so you just pip install NLU, and that's literally all the code you need to write. So let's see how we put this together now in the medical context. The first task that usually people are interested in is name entity recognition. And the goal here is to be able to read text and recognize relevant entities. So in the top example here, and you can see this is literally all the code that you need to do this after installation. This is a radiology example. Okay, so someone has done X-ray, CT, MRI, and we want to be able to extract things like what was the imaging procedures, what were the findings, what were the body parts, what were some of the key results. So you have a pre-trained model that specifically does that, if those are the questions you care about. But of course, maybe you're doing radiology, maybe you're doing other things. So if you look at the second example here, here we are looking at drugs. So for example, let's say I'm building an application that tries to look for medication errors, right, or potential conflicts or side effects. So I need to be able to read that here's what was prescribed to this person. And it's not enough to get the name of the drug. I need the strength, the dosage, the route, so how often you take it, where will you take it, how will we give it to you, and be able to normalize those items. So that's another kind of model that's available there. Let's go next. Thank you. Overall, there are more than 400 types of medical entities that Spark NLP for healthcare can identify just out of the box. And of course, this is trainable. So if anything is missing, you can train your own. So you can see some other examples. Social determinants of health and medical risk factors are very popular, right? So if you have a patient, you want to know, are they at risk for something specific, heart disease, kidney disease, whatever may be the case. So knowing whether they're diabetes, hypertension, obesity are very important. And in the example you can see below, we see something that's used in almost every project, which is de-identification, right? So usually being able to see the data at all and work on the data relies on the ability to de-identify it correctly. De-identification is one of those tasks where about 3 years ago, algorithms reached the same level of accuracy as human, as manual de-identification. So now a lot of what is happening in the industry is that hospital systems, software companies, basically whoever has access to this kind of data just de-identifies everything all the time, which is fantastic because it gives really much more access to data scientists. The other thing the identification does well is it removes some biases, because sometimes based on hospital names, even family names of doctors, you can have models that overfit on those. So I showed you that all of this works in one line of code, but there's the other important piece, which is like, how well does this actually work? What we focus on, and what really everyone, especially in healthcare, should focus on, is really being able to make sure that you deliver state-of-the-art results consistently. And state-of-the-art actually means something. So it's not a marketing term, it's an academic term, right? When people in academia say that, okay, we have established a new state-of-the-art for a benchmark, it means that, yeah, we've achieved better accuracy than ever seen before, but on a public benchmark that's reproducible. So we have 5 criteria for when we say, okay, yeah, we actually have a new state-of-the-art result. So it has to be a peer-reviewed paper, right? So not something that, a blog we published, but something that people actually reviewed and said, okay, this, at least on paper makes sense. It has to be on public competitive benchmark. So not a benchmark that we invented ourselves on our own data that looks nice on the model we did, but something that something else labeled, published, and that many other researchers compete on. Of course, the code has to be public so that any other researchers can go and reproduce it. Okay, because as I'm sure you know, there's a lot of way to make mistakes, right? Or cut, or only show the data that works well for you. We want to make sure that doesn't happen, because the whole point of science is that I do something slightly better, you read it, you improve on top of that, right? And then that's how we make progress, right? As a community. And with us, we also require for our own models that a model be actually used in production system and in multiple ones. So this cannot be something that will overfit for one specific data set or project, right? Something that's actually in use. And that's what we do. Click once more, thank you. So, for example, for clinical MNT recognition, there's a paper, it's actually been refreshed, because what happens when you have a new paper and you establish a new state of the art, within 8 weeks, someone will publish another paper and say, hey, they did okay, but I did slightly better, right? And that's really what we want. It's a very fast-moving field. It's actually super nice in that respect. So we have a recent paper that actually shows that on three of really the most widely researched studies on clinical entity recognition, so the 2010 I2B2, 2014 I2B2 for de-identification, 2018 I2B2 for medication extraction, we actually established new state-of-the-art accuracy with Spark NLP for healthcare with those models, and so that's actually available to you now out of the box. We've also shown competition with some of the public cloud APIs. So AWS Comprehend Medical, Azure has a healthcare API, Google Cloud has a healthcare API, and also this is public and shown directly in touch with all of those, with all 3 teams. We've shown that we actually make 4 to 6 times fewer errors than they do on some of the most common entities that people care to extract. So symptoms, diagnoses, diseases, body parts, and drugs. Next, thanks. So other than clinical name identification, the other task that's very popular in the healthcare side is what's called biomedical name entity recognition, which is, it's the same thing. So you want to recognize entities, but not from clinical notes, not from information written about the patient, but from medical research. For example, you want to summarize medical papers. Okay, why? Because there's 600,000 COVID-related papers that have been written in 18 months and no one has time to read them. And you actually need, it's a big data problem. You need computers to do it, to tell you what's the bottom line. Or you want to be able to match patients to clinical trials. You need to read all the clinical trial protocols to see which biomarkers and which personalized trials are actually available to a specific patient. So the text is very different. Okay, and as you can see here in the example, where there's several hundred models dealing with those kinds of text, that kind of language, and very often what you're looking for is genomics, so genes, gene products, gene expressions, phenotypes, mutations, proteins, and so on. So that's almost a completely different case. Outside healthcare it looks the same, but really it's as different as doing finance and legal, for example. It's completely different languages. And let's go to the next one. So this is another case where also we have a paper that's so almost 2 years ago by now, so we're working on updating that as well, that shows that in 8 out of 9 widely studied competitive biomedical benchmarks, we'll be able to achieve new state of the art. And really a lot of it, and I'm sure if you work in data science, you'll see it. Part of it is, yes, you have to apply the latest and greatest techniques, right? So for example, it used to be that you could do this with BLSTMs and CNNs, and that was state of the art until 2 or 3 years ago. Now a better architecture is around BERT for sequence classification, for example, right? That seems to perform well, but also very important is what kind of language models and embeddings you use. Right, so initially it was BERT, then it was BioBERT and clinical BERT, and now we've tuned our own models, and really it's then putting together the whole thing to make sure we can really squeeze every last bit of accuracy for those models and generalize them. Go on. So extracting entities is one thing you need to do, but it's really not useful for most use cases because when you identified an entity, for example, in this case, cancer, you need to tell people, okay, what is it that I'm saying about it? Okay, so there's a very big difference between saying, oh, this patient has cancer versus saying, oh, this patient does not have cancer. Right, it's kind of important to know whether they have it or not have it, right? If you're trying to say, oh, are they at risk? Should I refer them to something, right? Are they a good match for this possible treatment? It's also very common to say, oh, a patient's father had cancer, okay, which is clinically relevant. It's just not about the patient, right? So if you just mark the word cancer, you really, by itself, it's not very useful. So assertion status detection is another deep learning challenge, which is about understanding context. So we want to know when I'm saying something, is it positive? Like, so does someone have cancer? Does someone not have cancer? Does someone maybe have cancer? So maybe is very, very important in medicine. It's kind of the doctor thought this was important enough to mention, but we don't really know. Knowing whether something happened today or in the history, right? So if someone had a procedure, but a year ago or 10 years ago, that's interesting, but we have to know this is in the past. Okay, and of course, knowing whether something happens to you or to someone else. So that's the challenge here. And also, as you can see, one line of code that does, in this case, both the name entity recognition and the assertion status detection. Because what you do in NLP is you build pipelines, right? So you come and say, take the original text, split it into sentences, tokenize it, get parts of speech, recognize entities, then do assertion status detection, and then just give me the whole thing at once, which is what you see here. And can we move to next? Thank you. And then within assertion status detection, also there are several public academic benchmarks. One of the really most competitive and widely studied is from 2014, and to CITO. And as you can see also, we're happy to actually establish a new state-of-the-art accuracy in that space, and that's now available to you out of the box. By the way, all the papers, they're on archive, they're public, they're on the websites of the conferences that were there, and also on our website we have a list of all the papers. The way we measure this competitive, the way we know when someone beat us, Facebook has a public website called Papers with Code. That's basically a bunch of leaderboards. And usually in there you can go and you can see, you put your paper, you have to put code as well, so the others can reproduce it. And they have several, 5,000-6,000 benchmarks in all aspects of AI. And that's usually where you find out, right, where someone else has done better, and then you can contact them and work together. So the third important asset I want to talk about that you need really in almost every single use case is relation extraction, which is being able to understand relationships between entities and more specifically semantic relationships. So if you have a sentence like this, okay, someone has they have numbness in the left hand and they have pain in the shoulder. So if I just have the entities, like I need to know, so is the numbness in the hand or in the shoulder, right? I mean, we have, you mentioned multiple body parts and multiple symptoms, right? I need to know that it's the left hand, right? So I have the directionality, I have the body part, I need to be able to link them together. If I cannot link them together, there's very little semantically that I can do with this, right? From a clinical perspective, question answering perspective, knowledge graph building, kind of those classic use cases. There are more than 50 types of semantic relations that we know to extract. So you can see here in the example below, a super popular one is understanding temporal relationships. So when did something happen, right? Did something happen before or after something else, right? So, did this happen after the procedure or before the procedure, right? During, really to be able to understand the patient's story. So now we are at the point where with fairly high accuracy, we can do those things automatically and answer those questions in a good way. With relations, what's really important is understanding the semantic part, kind of what is the relationship, not just the fact that two things are actually related. So for example, if I have a symptom and a procedure, right, or a treatment, right, I need to be able to tell between, okay, you know, we did this thing to you as a patient and it helped, or you can see in the sentence, we did this thing to you and it actually made it worse. Okay, those are two very semantically different things that you need to be able to differentiate between them. The good news is if you combine current language models, current transfer learning techniques, and also sometimes some label data as well, and we have about 15 doctors on our team who also annotate data and verify things clinically, you can answer many of those questions in an interesting way, in a fairly accurate way. Similarly, you can see the example below. Sometimes you want to read patient notes, sometimes you want to read medical research. And for medical research, you want to understand things like drug-drug interactions. Okay, for example, if you're studying, for example, vaccination side effects, right? If you're trying to understand interactions between, for example, different genomic biomarkers, right, and how they actually express themselves in humans, then you don't just care about paragraphs where both a gene and a symptom are mentioned together. You care about specific semantic relations, right? Oh, I want to understand if this happens to people with this gene, yes or no. So we are often, but not always, able to extract that. So within relation extraction, also there's been a lot of progress in terms of what you can actually achieve accuracy-wise. And one of the things that are really super exciting in this field is how far accuracy has improved, even in the past 4 or 5 years. And it feels like every year there's like a new revolution. And for us, it's also, I mean, it's a lot of fun, first of all, because we get to play with all the cool new toys. But other than that, what we find ourselves really re-implementing every year. Okay, so and that's a challenge, right? If you say that you do something state of the art today in anything in AI, usually 6 months later, whatever you built is no longer state of the art, right? There's something slightly better. And really what we find is usually every year we completely re-implement. So different neural network architectures, different transfer learning approaches, which means that things are faster, things are more accurate, and also very importantly, things require far less training data than they used to get to that level of accuracy. Yes, also there's the paper here, you're welcome to see it. So I just wanted to cover really some of the basic tasks that you need if you're doing anything with medical text. So recognizing entities, recognizing assertion status, recognize semantic relationships. 2 other important things that would be useful to you are being able to normalize entities. We didn't talk about that, right? So knowing that diabetic and diabetes and T2, DM are actually the same thing, right? So you can ask a question like, oh, give me all the diabetic patients, and you actually get the correct response. Simple stuff like that. And overall de-identification is another thing that's slightly more complex than I made it look here, but really being able to de-identify large bodies of patient information as accurately as people and at scale is also another thing that's super useful in practice. If you want to learn more, there's an NLP summit coming up in 3 weeks, which also Anna and the formulated by team is helping us put together. And if you really want to play with it, if you just Google Spark NLP or you go to the link here, there are more than 300 free and open Python notebooks. They run in Colab, so you can run them yourself, right? So you can put in your own text, you can try the model, you can change the pipeline, you can see what works, what doesn't work. State of the art does not mean perfect, right? It means this is as accurately as we can get with automated system today, at least in the peer-reviewed sense of the world. But you definitely want to see what fits your use case, what doesn't, how you can tweak and tune your own. 2 super interesting things that are happening now this year are, first of all, no code. So 1 line of code is nice, but there's a big difference between that and 0 lines of code, because 0 lines of code means that like none of us need to get involved, right? And now we have tools and we have models that were built by medical doctors, so no data scientist was harmed in the creation of this model. And there's more and more of that that's happening as well, right? Where you can actually take all of the training pipeline, the best practices, the optimization, and just automate it all away. So that's one thing that's really, I mean, like in the past year, it's the first time I've seen, people have been talking about this the first time, saying, oh, there's quite a few models that were just trained by doctors, by pharmacists, right? Really without data scientists being involved. The second cool thing happening this year is zero-shot learning. And zero-shot learning is a form of transfer learning that's very similar to how you teach humans to do things. Basically, there's no label data. There's no training data. You just give people an example, right? So the classic example of zero-shot learning from computer vision is you have a model in order to identify horses, right? And you just give the model a prompt. You tell him, oh, look, a zebra is a horse with black stripes, okay? And that's it. And now you show them a picture, you come and say, what is this? And they should be able to come and say, okay, this is a zebra. And zebras are nice. Being able to identify cancer tumors is even nicer, right? Or pneumonia, right? Or progression of heart disease. That's even more important. And also, what it enables you to tune models to specific use cases much, much, much faster than it was done before. Okay, and also in a much more natural way. Especially when you're working with people who are not technologists, it's a very natural way. It's basically when you, the way you tell people to build the prompt is really how would you explain this to another person? Okay, and you try different things and you see what works. So you'll be able to hear more of that in the NLP Summit, and also these are some of the tools we keep working on, so they can give them to you. A lot of them is free and open source, really as much as we can. Some of the healthcare stuff, unfortunately, we just cannot because something needs to fund the open source. What I would appreciate is if you're doing projects, if you're trying things, if you have things that you want to be able to do, please get in touch. I'm also interested to know what people are building, really so that we know what we need to build next for you. Thank you.